So, Mr. Lychee, you've been going through all sorts of stuff. It's been very slow. I heard a few are 55 minutes. I don't know how you do it, but good on you. Mine is going to be a lot faster than that. So, we're just going to make this pretty snappy. So, this is what my game looks like. We have our angles working pretty well. If I hit at the top, it goes up. Hit at the bottom, it goes down. Hit it midwise, it goes more horizontally. We got points working. We got a rally counter. Yeah, just all the essentials of Pong. And I'll speed up this. As you can tell, I'm no Pong pro, but it works. Pretty solid. So now we're going to break down the code. Yikes, this is bright. We're going to go into VS. Inputting libraries, blah, blah, blah. String stream. Windows was being really annoying about the toString method. Where is it? Right here. toString. My version of SFML didn't like that. Or not SFML, just my version of everything, C++ and code blocks and stuff. So I use string streams for this. It's pretty simple. I was just piping in the value and then getting the string version of it. And then setting that, and then making sure to reset so we don't end up with something goofy. So, this is system variables. So because we're on Windows, it's this. I just kept having to switch back and forth, so I figured out a way to do it. We're on Windows 32. If I was at school, it'd be on Linux. And that's just setting our velocity and paddle speed. Creating the window, and then ball, set the origin, position, color, radius. We got our icon. It's that silly little Obama pyramid, and it also shows up here. I just wanted to mess around. We got our paddle, and its size, color, origin, position. Second paddle, loading a font so that all the text works. Making sure that the text is in the right spot, and it's bold. We got a rally text. We got P1 scored P2. We have our, this is just a little indicator text, because I felt like the number in the middle might have been hard to read, so I just made sure there was a little thing telling you what it was. So these don't need to be long elegant, but this one definitely does, because let's just say you have two of the best Pong people ever. Gotta make sure that they can play forever, or for stupidly long time. We have a clock for interaction later. I'll explain that when we get to it. It's just letting you close the SFML window when the person clicks the close button. And if you don't have this, it'll complain about Windows not responding. This is just if it hits on, like if it hits the right side. So like if it is a point for player 1, then we want to add to the score, flip the velocity so it goes to the person who got the point, because, you know, winner's choice. Set a rally back to 0 because, duh, it's not a rally if you aren't rallying. And then set the ball's position to the middle of the screen, roughly. Actually, exactly, because we have the origin. And then we have, if it hits the left wall, so if P2 got a point, we are adding to their score and updating it. Setting rally back to 0, the exact same stuff. If it hits the top or the bottom, just flip it, and you're good to go, because we just want it to bounce normally. There's no crazy bouncing going on. Movement, pretty simple. Removing the paddle speed. If they press W, and if they're not too high up, they press S, and they're not too far down. Exact same thing for arrow keys. And then we have intersection, so when it actually hits the paddle. This is very technical. We're going to go one step at a time. So first, we're going to reverse the velocity X. If it's heading towards player 2, we want it to flip and head towards player 1. We have our relative intersect. So basically, we get the position plus half of the size to get like the direct center of our paddle. And then we subtract the ball's position to get like, was it higher than the center, like more up on the screen or more down. Um, and then we normalize that by -1 and 1. So basically just divide it by half of layer 1 so that we end up with -1 to 1 instead of a huge amount. And then we have our bounce angle, just taking our relative intersect. 1 to 1 doesn't actually exist. We want it to be from -90 to 90. So it'll bounce either like directly up or down or anywhere in between. So this is pretty simple. A squared plus b squared equals c squared. And then we have changing it to radians because the sine function works with radians and it's what it's expecting just by default. So it's just multiplying by pi, 50 digits, because got to be precise, divided by 180. It's just the way to get radians. Angle times pi divided by 180. And then we're setting the actual velocity.y to negative speed times that sine of angle. So that's a lot. I'll go through an example at the end of this because we're about done. This other thing is basically I was finding that sometimes it would collide for more frames than I was expecting. So we end up 3 from just hitting it once. Like you'd add 3 to rally. So basically said if it's only add it if it's greater than 5 seconds and then restart whenever you add. Because you're never going to have each person hitting it within 0.5 seconds at the speed that I'm doing it at least. And so this one is the exact same as the previous, just with player 2. Because we're always going to want to flip the velocity x to have it going the opposite way. And that makes it work with whichever one we have. But we just have setting the string of rally text, using a string stream again, because Windows, or at least my instance of code blocks, is not liking std2string. It says it doesn't exist, when it clearly does. Afterwards, I just have small score offset fixing, just to account for when it switches from single to double digits, just to make it look a little nicer. And then this is clearing the screen so that we can display everything. And so if it's equal to game over, we only want to show the game over text, and we want to show it directly in the middle of the screen. Elsewise, like if it's part of the game loop, getting the ball's position, changing current position by the velocity.x and velocity.y variables, and then setting the ball's position to that, and then drawing it all. And then display, so it actually updates the window. So now I'll get into an example of how this works. Alright, so I'm back with the most technical tool of all time, MS Paint. So we are going to look at an example. So we have paddle 1, and let's say it has a y of 20, and its height is 10 units. And we have a ball that's going to hit directly on the center point, right? This ball, let's pretend it's going at a velocity of -1.5 and a y velocity of 1. So our first step is here. When it intersects, we want to figure out all this as soon as it touches. No sooner, no later, just directly when it touches. First of all, flip the velocity. So it's coming in at -1.5. If we flip it, it'll leave at 1.51. So it'll do what makes sense in actual science, and just angle of incidence equals angle of reflection. But we want to take it further, because that's kind of boring for a Pong game. You can't really control it that well. So after this, we have 1.5 to 1. And so you want to calculate where from the center the ball hit. So here, it hit the exact center. Our paddle's position is 20, plus our size divided by 2, 5. So 25 minus the ball's position. 25, which is this point right here, minus the ball's y position, which is going, when it touches that, it's also going to be 25. So the next step is we are going to normalize that so that we can use the angle that we want to. That equals 0. So we're going to say 0 divided by half of the size of the paddle. So divided by 5, so that we can get a range from -1 to +1. So 0 divided by 5, though, is just 0. So now we're going to get our bounce angle. So we're going to take that 0 and multiply it by 90, which gives us 0. Duh. So next, we want to figure out the exact speed that we want coming out. So we're going to take A and B. So this is going to be A, this is going to be B. And this is the hypotenuse, so it's C of the triangle. Because this is A, this is B, and speed will be C, right? So A squared plus B squared equals C squared, Pythagorean's theorem. It's how we're going to figure out this so that we can convert it back out. Currently, our velocity is going to carry us like that, right? So even if we're right here, the velocity is the exact same at the start. So it'll be this exact velocity. We have 1.5 and 1. We're going to do A squared plus B squared. So 1.5 squared. So that's 2.25 plus 1 squared is 1. Means that our C squared, so this all together is C squared, right? Means that our C squared is going to be 3.25. And then we're going to get the square root of that because we want C. We don't want C squared. So the square root of 3.25 is 1.8. So that means that this right here is 1.8. Right? And in order to figure out where we should be going, we're going to use that 1.8. So next we're going to take the bounce angle that we got earlier, right? Which is 0, because we want it to go straight back out. We're going to multiply it by pi divided by 180 to get the radians, which is just another way of representing degrees that our sine function expects, because this is doing sine in radians. So we got our radians, and then we're going to multiply it by negative speed. So this is 0 times pi divided by d, so it's just 0. So our radians is literally just 0. And our speed currently is this variable. So our speed is going to end up being negative 1.8 times 0. So it doesn't matter. We're going to multiply it by 0. So our velocity.y is actually going to be 0. So we don't want to move on the y-axis, which means that we're moving along in the x. So we'll shoot out this way. And that's it. So our x, if you don't remember from earlier, is just flipped. So because after all that our y ends up being just 0, our ball just ends up going directly outwards. It's not a straight line, but you can imagine it goes directly straight back, like straight across your screen. If we want to do if we wanted to do that with a non-zero value, I'll put that up on the screen now. And yeah, that's basically it. Thanks for watching, Mr. Lychee.